Hello, everybody. We are on week 7, and today we will continue on gradually varied flow for hydraulics. And I am going to introduce you an interesting topic. Uh, First, you are going to learn the flow over uh, large waves. Then you will also learn that what happens if the flow experiences a hump on the bottom. So uh, today's topic is a little bit difficult, could be a little bit difficult to follow, guys. So I want your attention. Just be careful, listen carefully, and please ask me any question if you need um, any clarification. So I like to start with a video from YouTube. This is actually a kind of experiment conducted in a lab, in a hydraulic labs. We have almost a similar equipment, but because of pandemic, we are not able to conduct the experiments by ourselves. Anyway, I will try to do the arrangement for the next second part after the spring break. I think the spring break is not next week, the following week, isn't it? We are going to have lectures on next week, then we will have spring break. Is it correct? Or next week is the spring break?
We'll have lectures on the next week and then spring break.
Then spring break. Okay, this is what I know also. Thank you, Ruslan, for clarification. Okay, let's watch this video, and I will continue. Okay, it is 2 minutes and half. Okay, guys, now I like to make an explanation what's going on here, because this is a kind of silent video. There is no voice, like voice. So you see that there is a kind of flow channel here. It is a kind of experimental setup, and flow is approaching to a kind of, it's a hump, but we will say that it is broad crested weir. Okay, broad crested weir. It means that the top of the weir is not sharp. The top of the weir is broad, and when the water approaches it, okay, just I will continue, but I want your opinion. What do you think that the height on the top of the weir is going to be higher than the original height on the right side, or it is going to be lower than the original height on the depth on the right side? What do you think, guys? Do you have any idea? I mean, maybe you can make a kind of, I mean, just you can capture it from the uh, specific energy curve. Do you have any idea what's going to happen? How this flow is going to pass over the weir? Is it going to pass over with a higher or lower height than this? Any idea? Okay, anyway, let's see that what's going to happen. It might be surprising for you. Okay, this is exactly the point we are going to highlight today, and have a look at that. This is a kind of broad crested weir, okay, and water passing through over it, okay, passing over it. And this is the depth of the water, but while it is passing over where, see that there's a fall in the depth, okay? So it's not going up, but just the opposite, it is going down. It's quite interesting, isn't it? So this is a kind of specific case. You are now going to learn that why this is happening and how you can make, I mean, calculate what kind of calculations we can do here. And also at the later part of this lecture, if time allows me, I am going to explain that how you can make a kind of calculation of water passing a hump. Hump means a kind of extension on the bottom, okay, like this one, like a weir. It's not necessarily to be broad crested. It could be a kind of just a simple hump. Anyway, let's see what's going to happen in the experiment. Then I will explain you the details. Okay, if you observe river flow, you will see lots of waves, and the main reason of those waves on the river is mostly the humps or some stones on the ground. Okay, if there is a stone on the ground on the bottom, the river flow is experiencing a kind of change in the depth, as you see that. So it comes over here with subcritical flow, and here it turns into again subcritical, and it continues. And you may also say that there's hydraulic jump here, but I am not pretty sure that if it's hydraulic jump, it seems that this hydraulic jump. If it's a hydraulic jump, this is not a kind of subcritical flow. Maybe it's supercritical flow. But this is a very interesting case about energy, specific energy of the system. Okay, guys, I think you see that there is a kind of 5 millimeter difference in the height from the downstream and upstream after experiencing a kind of obstacle on the river basin or flow basin. Do you know that what is the reason of that 5 millimeter loss or 5 millimeter difference? Do you have any idea? Look at here. It is 135 almost. It is downstream, and in the upstream it is 140. It means that there is 5 millimeter difference. Do you know that what it is? Why we have 5 millimeter difference in the flow in between upstream and downstream? It is a very simple question actually.
Maybe it's energy loss.
Yes, exactly. This is energy loss. So it seems that 5 milliliter of head is lost because of that obstacle. I mean, it is a crest. Why I mean broad crested wave, but it is still an obstacle obscuring the water and dissipating some energy. And it is the case again. See that when the water experiencing a kind of obscure or obstacle, a kind of hump on the bottom, then the water level will go down. Okay, of course there are some other possible ways it can come back, it can bounce back or some other stuff. We will deal with those things in the coming lectures, but today we are going to focus on this, and you will learn that how we are experiencing a kind of water drop in the depth while the water is passing such a kind of broad crested here. Okay. So that type of structures are called overflow structures, okay, guys? And here, this is the kind of presentation in graphical format, what you have just observed. And in theory, while a water is passing over a broad crest, the height on the crest is supposed to be equal to critical depth. Okay, so what you have seen on the high as a height on the crest is the critical depth. Okay, it is a critical depth if it experiences a fall after. Okay, if it experiences a fall after the crest, you are going to see that it is going to be the critical depth. I will explain you. And anyway, in the next slide, I'm going to open the specific energy graph, and I will explain it why this is happening in that way. And another alternative is that free fall. See that water is flowing over here and experiencing a free fall. So in theory, we will say that a close vicinity to the tipping point or the ending point of the crest or the channel, you should have the depth of critical depth. Okay, so somewhere around here, around 3 to 4 y critical distance of L, you will have a kind of depth of water which will be equal to critical depth. This is another application. Which is a free fall. This is a broad crested weir. So let's have a look at that, why it is happening in that way. Well, this is not the one that I like to show you. Just right here. Okay. Okay, anyway, let's continue by solving one question, then I will explain you details with energy flow. So this question is a very simple question actually. It tells us that, okay, it is asking that there is 1 meter wide channel and the depth of water is also 1 meter. So typically the area of water, flowing water is 1 times 1, which is 1 meter square area. And the flow rate of the flow is given also as 0.26 meter cube per second. So you just realize that the velocity of the flow is equal to 0.62 meter per second. And the slope is given and Manning constant is given. So if you see Manning constant, it is not surprising that you will solve this problem by using Manning equation. And the question is asking that the channel terminates in a free discharge. It means that the second case, okay, free discharge. And the question is that find the normal depth. It means y0, find normal depth and the depth in the vicinity of the discharge. So typically this question is asking us what is the critical depth of the flow. Okay, so you are going to find y0, then the critical depth of the flow. That's all. Okay, there is a typo here. I am correcting it, guys. It's not 1 meter because we are supposed to find what is the depth of the water. Okay, so let's have a look at the water channel is 1 meter wide and the flow is given. We cannot calculate the velocity at the moment. We will find it. So the equation is, the solution is quite a simple. Actually, I asked a similar question in the midterm exam. I don't know how many students answered it correctly, but in order to use the Manning equation, first you should calculate the hydraulic radius. The hydraulic radius is a kind of parameter. It is wetted area over wetted perimeter. So wetted area here is 1 times y0, and the perimeter is 1 plus 2 times y0. And hydraulic radius is this, basically. Okay, and we will also say that you can calculate the velocity, okay, by using this Manning equation, and the velocity is equal to flow rate over area, and this is flow rate, and this is the area, 1 over y0. And if you put everything into the equation, you are going to end up with this equation. So it is a little bit complicated to solve such equations numerically, but I suggest you to give a kind of trial and error. Start with given a number like 0.5, then you will go and change the number and you will find the solution by making iterations. It is possible. Then at the end, you are going to find that y0 is going to, is 0.57 meter. Okay, so the depth of water in this channel is 0.57 meters. Actually, this is exactly what you have learned so far. And again, I am repeating that I asked almost a similar question without free fall part in our midterm exam. And the remaining question is that you found the normal depth and the depth within that discharge. The depth within that discharge means that you should assume that it is equal to y critical depth. So you will find the critical depth by using the equation, and then critical depth is 0.34 meter, and this is the answer of the given question. So you should report all of them, and it's full solution. Okay, so after solving this problem, I think it is time to explain you how we are experiencing a kind of decrease in the depth. Okay, guys, this is what we have. Okay, this is what we have, and we have a hump here. Actually, this is a kind of, also you can consider this hump as a kind of broad crested weir. Okay, this is exactly the same thing, and the water is approaching to that hump, and after experiencing that hump, you are going to see that there's a water drop. Okay, the depth height dropped in the system if this flow is subcritical. And let's analyze it on the energy flow. Okay, specific energy chart. Okay, please have a look at specific energy chart. I am pointing out on the screen, and follow my cursor, please. We are on subcritical part. Subcritical part is that, okay, I think I can use annotation right here. Okay, subcritical part is the part over this. Okay, oops, I am sorry, I don't have proper equipment for now. Okay, this is our threshold value. This is for critical depth, and this is critical depth. And over this depth, any value, any depth is subcritical. Under this, lower this value, it is supercritical flow. So in our case, now we are focusing on subcritical flow. In our case, if it is subcritical flow, this is your case in the first point. Okay, this is your case in the first point. And experiencing a hump means a kind of theta z amount of y should be reduced. It means that amount of theta z of y from the energy, you are going to reduce it. It means that you will end up at this position. Okay, so this is position 1, this is position 2, and let's have a look at the energy, specific energy curve. For point 1, the specific energy curve indicating that y1 is your original depth, and when you go to position 2, after reducing theta z, the height of the hump, it is height of the hump, and then you are going to see that you will experience just a little bit lower value than the original depth. It is going to be y2. And I think you just realize that if the water is supercritical, okay, if the water is supercritical, then this is your case, and adding a theta z means that you are going to have slightly higher depth than the original depth. So the question is this: you are making an observation on the water flow, like in the experiment I just demonstrated in the video. It is just demonstrated in the video at the beginning of the course, and you are making an observation, and you see that after experiencing a hump, if the water level is increasing, so what you will say? Would you say that the water is subcritical or supercritical?
Supercritical.
Exactly, it is supercritical. If you observe that water height or water depth is falling, okay, dropping, then you will say that this flow is subcritical flow. And I want you to have a look at those energy equations, okay, for subcritical flow. Anyway, today I am going to solve one problem for you for subcritical flow. Then I will focus on the supercritical flow on the next time, okay? Because there is also another thing you should consider, that if it is bouncing back or not, okay? So anyway, let's not make complicated. for today. I will continue on on Monday, next Monday, on this topic. But today let's focus on subcritical flow only. So the original equation for point A1 is equal to, I mean, specific energy equation is equal to y1 plus, I mean, depth of the water plus velocity at 0.1 square over 2g. This is our original equation. And for the point 2, okay, basically what you will do, you are going to subtract this height from the total energy. So the specific energy at point 2, okay, specific energy at point 2 is equal to specific energy 1 minus theta z. It means height of the hump. Okay, guys, if you remember this simple equation, I think you can solve any problem. Okay, and after this, you can either write what should be the specific energy at point 2, okay? Then you can solve any problem as it is given. Okay, do we have any question on this part? And please carefully check the specific energy diagram and try to understand that why we are reducing theta z, okay? Because we are reducing the, I mean, we are removing that amount of energy from the system because of the hump. Water, there is no water here. But still, I mean, maybe in theory, I mean, if you didn't, I mean, if you did not introduce this theory, maybe you will say that after experiencing a hump, there should be a kind of rising up, but this is not the case. If the flow is subcritical, it always goes down, okay? If flow is not subcritical, the water flow should go up if it's supercritical. And one more thing, you should also check it out that if Y critical is reached or not, okay? For example, if after experiencing a hump, if your depth, theoretical depth is lower than Y critical, I think you just realize that there is a kind of change in the system. It means that supercritical flow will turn into subcritical flow. And just the opposite is also interesting case. So that's why those cases are going to be assessed further, even the original height will be different in such cases. Okay, I am going to explain everything step by step. So in that type of problems, I mean, experiencing a hump type of problem, there are 4 cases. The first case is that the water, I mean, the upflow water can pass it without having any rise in the original height. I mean, Y1 can stay as it is, and then you can experience a kind of lower depth on the right side, or it can, again, there will be no rise, but you may have a kind of increase on the right side. Okay, it is the second case for supercritical to supercritical flow. And the third and fourth cases are the original flow cannot retain its height because of the critical flow change. I mean, subcritical may turn into supercritical. In this case, a certain amount of flow will back up, and then you are going to have also a rising up on the approaching point of the upflow regime. Anyway, these are some other details, a little bit complicated stuff. I am going to explain you them later, okay? But just today, you should focus on this case only. So just assume that we have subcritical flow, it's approaching, and it is just passing by the hump by having a kind of decrease, okay? So original height will retained, but the second height on point 2 is going to be lower than the first case. So it is exactly this case, okay? The first flow is subcritical and the second flow is still subcritical. It means that the flow on the downstream is still higher than critical depth, okay? It is possible that that flow could be lower than critical depth. In this case, there will be other issue. It means that you cannot retain the original height on the upstream flow. It should be recalculated. It's going to be different than the given flow. So this is, I think, these kind of cases are the most difficult cases to solve, and this is one of the easiest case. Okay, repeating again. Now we are going to focus on this case only. The flow is going to experience a hump on the bottom, and it is subcritical flow, and it's going to pass the hump, still retaining the subcritical flow conditions, but the depth of the water will be reduced, okay, because of the specific energy characteristics of the system. And this system is exactly given on this specific energy 0.1 to 0.2. That was that amount of reduction, but it is not as much as a reduction that you are going to reach until the critical depth. Okay, in theory, is everything clear? Only for this case. Guys, this is not an easy topic, I know. But if you do not answer, if you do not respond, if you do not comment, it means silence. If silence is not broken, I will accept that you did it. You understood it. Then I will
Sorry, could you repeat, please?
repeat of what, Rasul? The cases.
The question, yeah.
Okay, let's have a look at. No, I am asking that. Did you get the theoretical explanation of this case?
I guess the deeper we'll go, the more we'll understand. But for now,
yeah. But there are 4 different cases. Okay, we are going to handle 4 different cases. But today I am only going to focus on subcritical flow. Will experience a hump on the bottom. Then it's going to decrease, but still flow will be subcritical. Okay. This is the case now we are handling. In this case, if you look at this energy curve, you will see that this is position 1. This is position 1. Okay. Follow my cursor. It means that we are going to experience a delta Z reduction in the hump, and you are going to lose that amount of energy, and your flow depth is going to be lower than the original depth, but still you are in the zone of subcritical flow. Okay. This is the first case we are going to handle. And the second case could be supercritical to supercritical. Third case is subcritical to supercritical. It is still possible. And the fourth case is supercritical to subcritical. So these are the alternatives, and the last 2 are very complex and complicated. We will handle them later. But today we will only focus on subcritical to subcritical case passing over a hump. Okay, so no questions. I will solve one problem, then I think everything will be over for today. Okay, so the problem is this. So we have a rectangular channel, and the width of the channel is 2 meters. And it carry a discharge of 4.8 cubic meter per second. And the original depth is 1.6 meter. Okay, it means the depth on the upstream flow. And you are experiencing, this flow is experiencing a hump. It is smooth. Okay, this is quite typical setup. And then the height of the hump is given as 0.10. So the question is asking us that ignore everything in terms of energy losses and other stuff, okay? And just calculate that what should be the height on the hump. Okay, in such questions, the first thing is always first, you should check the flow conditions, okay? So let's go step by step solution, and I think you will understand what I mean. Okay, the first thing is that let's first calculate the velocities. Velocities are easy. You can calculate the velocity on the left side, okay? And also you can calculate the velocity on the right side, but on the right side, we don't know what is the depth. So that's why we are going to give it as an unknown. But the velocity on the left side is calculated as 1.5 meter per second. It's easy. It is flow rate over area, okay? And it is easy to calculate the Froude number. And for the upstream flow, I calculated here for you the flow Froude number. It is velocity 1 over in root squared gy1, and it's equal to 0.38, means smaller than 1. It is subcritical flow, okay? So if the flow is subcritical, the second question is that if it is going to still stay as a subcritical flow after the hump, okay? This is what we will look for, okay? This is what we will look for. So that's why let's calculate first the energy, specific energy for 0.1. And the specific energy at 0.1 is easy, y1 plus velocity square or 2g, and it is equal to 172 meters, okay? This is the specific energy. And as I told you that, while you are calculating the specific energy at 0.2, it is quite simple. You should subtract the height of hump from the specific energy of 0.1. So the specific energy at 0.2 will be 1.62 meters, okay? So far, so good, right? Guys. And at this point,
yes,
at this point, you should check, okay? You should check what should be the critical flow on the right side, okay? What should be the critical flow on the right side? And it is easy to calculate, as you remember that I gave you another equation which can be calculated by q, I mean small q, but still you can use the same equation, okay? I mean the conventional critical depth equation. And if you calculate the critical depth, you will see that the critical depth is going to be 1.62 meters. 1.62 meters. This is the critical depth. Sorry, the critical depth is going to be 0.84 meters. Sorry, 0.84 meters. And this 0.84 meter is larger than our specific energy. Okay. If it is larger than our specific energy, let's go here, that graph. I will show you that. Okay, let's go that graph. This is our specific energy. Okay. And it seems that our total energy is larger than specific energy. I mean, the minimum energy, critical energy. So it means that we are still having a subcritical flow. Okay. So if you are having subcritical flow, the conditions are in that way. Subcritical flow experiencing a hump, then it stays as a subcritical flow. And in this case, it's quite simple that you should calculate the depth by using the specific energy equation, and you will put everything in this equation. And your height specific energy equal to 1.62. You calculate it here. And if you calculate the Y2, I mean the second depth on here, then you are going to find 3 alternative solutions, as you know that in our earlier cases. And this solution will give you 3 numbers. One is negative, two others are positive. And these are alternative depths. And here the critical question is that which one you are going to select. And you just confirmed here that this flow is going to stay as subcritical. That's why you should select this one, okay? Not the supercritical one. So you are going to select the subcritical flow, and your new depth is going to be 1.46 meters, and it is 1.61 meters, and you have 0.10 meters here, okay? And it means that only 10 centimeters left on the top of the equation. So it means that you are going to experience 10 centimeter fall in the depth of the water if you experience a kind of 10 centimeters hump on the bottom. So you see that the question is quite simple. Again, after just showing you that the solution, I am repeating that while you are solving these problems, the first thing is that you should check what is the flow on the upstream, if it is subcritical and supercritical. Okay. Then if after deciding that if it's subcritical and supercritical, then the second thing is that you are going to calculate the energy, specific energy of the condition 1, and then you will calculate the specific energy for the condition 2, and then you should calculate the critical depth for the condition 2. Okay, for condition 2, after calculating the critical depth, you should compare it with the total energy, specific energy for the point 2, and if the specific energy of point 2 is larger or smaller than the depth, critical depth you calculated, you will decide that the flow is subcritical or supercritical. Okay, so everything is as that simple. You are going to identify the flow conditions, if it is critical or subcritical in upstreams and downstreams, then you are going to make the calculations. I am repeating for you. In this case, for today, we are focusing on subcritical to subcritical. So in subcritical to subcritical, solution is easy. If the flow is in different state, like subcritical to supercritical, or supercritical to supercritical, or supercritical to subcritical, there will be different solutions. Anyway, I'm going to cover them later on the coming days. Okay, that's all for you guys today. Any questions?
Okay, thank you.
So this is a little bit difficult topic. I think it is one of the most difficult topic in hydraulics. So please focus some time. And also in Yunus Çengel's book, there are lots of problems. Just focusing on this particular problem. I mean, if I were you, I will spend some time during the weekend and try to make some practice and understand the concept. It's going to help you to understand everything in a better way. Okay, guys, it's over for today. I'll see you next time on Monday. Bye. By the way, I am going to mark your midterms as soon as possible. Most probably, it is going to bounce back until end of the spring break. So I am not expecting to make an announcement for all the marks in this week or maybe next week, but most probably in the break time, I am going to sort it out. Okay, be patient, guys. Be patient. I will do it.
Okay, thank you.
Okay, thank you. Thank you. Bye bye.